I am not of German origin. In fact, I come from a country, Italy, which has a traditional rivalry with Germany, especially in soccer, but in all kinds of other things as well. However, whether you are from Germany or not, one must admit that Germany has a great culture, great history, and has left the world with lots of very wonderful gifts. Sometimes we tend to focus on some historical periods that were not very flattering for Germans, but we have to remember Germany has given lots of other things to the world. Things like beer and Oktoberfest, which, even though originated in Germany, it's celebrated throughout the world, or great music and great art in general, and yes, great mathematics. You may want to find out who that fellow is. I'm sure you all know who the guy on the left is, but see if you can find who the guy on the right side is. And now, why am I telling you all this? Well, because the topic we're going to deal with today is the topic of eigenvalues and eigenvectors. Those are two strange words, and they should sound strange because they're a mixture of a German piece and an English piece. So eigen, in fact, comes from the German language, and it is translated somewhat like something special, something characteristic, something own, peculiar to whatever it is you're doing. In fact, it's a word which is so untranslatable in a way that mathematicians have decided to keep it in the mathematical jargon. So what we're going to do now is a little bit of introduction, and then we're going to see what these eigenvalues and eigenvectors are and in what sense they are peculiar characteristic of what. Before we dive into this concept of eigenvalues and eigenvectors, I want to put it in its context, which is a very general mathematical context. The question of eigenvalues and eigenvectors stems from a very wide ranging kind of mathematical problem that goes like this, and it's a problem related to functions. Okay? And the question is like this: if you have a function of whatever type it is, okay, are there some values of the input x for which the output is equal to the input? Okay. So in other words, does the function intersect the line y equals x? Now, in the context of calculus, actually, this is not an extremely interesting question of basic calculus, but it turns out to be a very interesting and very far-reaching question to explore, analyze, and find a solution of. Okay? So it is entirely possible that you're going to find it again in some future math courses. Okay? Now, the solutions of this kind of problem are usually called fixed points or stable values. And that's, in a way, what we're going to be looking for here. We're going to look for fixed points of something. Okay? So, in fact, what we're going to do is we're going to consider this particular question for matrix transformations. Remember, a matrix transformation is a function that changes one vector to another. And so what we're going to be asking is, well, are there some transformations for which the output is equal to the input, at least in some cases? Now, even posing the question in this way tells you right away that if we're doing that, we're going to look at matrix transformations that use a square matrix. Otherwise, the input and the output will not even have the same dimension. But assuming that that is true, are there some such vectors? And what are they? Can we find them? That's the thing that we're going to be looking at. Okay, I lied to you, but this is linear algebra. We can't keep things too specialized. We're going to generalize. Once we attack the problem of fixed points, well, we want to really do it a little bit more generally. Okay, so how are we going to do that? What question are we really going to ask? A slightly more general question. The question is the same as this one. Given a square matrix, A, and I said the question in the context of transformations only makes sense for square matrices. And let's say we have a real number lambda. Now this is a Greek letter, another Greek letter. You're going to learn the whole Greek alphabet by the end of this course. Are there vectors for which if I multiply a times this vector x, that I get the same thing as lambda times x? Now notice that if lambda is equal to 1, this is the fixed point problem, right? So ax equals just x, but we're generalizing it. We're just saying, well, not necessarily with just 1, but with lambda. What are we looking for here from a visual, practical, geometrical point of view? It is the following. Let's say we have a vector x, and just for simplicity I'm going to do this in two-dimensional Euclidean space, but again that's just to give you an idea of what we're trying to do. Now if I apply the matrix A to this vector x, that will give me a different vector, which generally is going to go in a different direction and probably have a different length as well. what we're looking for are any vectors which actually may be stretched if lambda is not equal to 1, but are going to maintain the same direction. So in other words, applying the matrix to X has the effect of simply stretching that vector. So what we're looking for are vectors whose image under the linear transformation is parallel to the original vector, just of a different length. Now, if lambda is equal to 0, then notice that what we're looking for is just the null space, because we're asking for lambda equal to 0, are there any vectors x such that a times x is equal to 0 times x, which is just 0. Okay, so you can tell that at least in this situation, the vectors we're looking for form actually a vector space, the null space that we've seen before. Another little thing, if for any lambda that I may choose, x equals 0 is always a solution of the problem, right? If I want my lambda equal to 0, then 0 always works, because of course a times 0 is going to be equal to lambda times 0. And that's kind of a duh kind of solution, and so we're not going to look for that one. We know that that exists, and that would make the problem fairly stupid. But what we're going to be looking at is non-trivial solutions. Okay? So in general, for any lambda which is not 0, or sometimes even for lambda equals 0, we'll see that later, for any lambda whatsoever, what we're going to be looking at is non-zero vectors which satisfy that equation. Okay? And we're going to see what we come up with.